Good morning, guys. My name's Sokol Maturi, and I'm here today to present our group Chrysler Carnage's approach to non-repetitive gameplay using artificial intelligence. Our group consists of two wonderful artists, Miko and Rob, and several very talented programmers, Alejandro, Elena, myself, and Tintin. Before I get on to our actual implementation and idea on how to implement the AI, I'd just like to take a quick second to explain what we mean by non-repetitive gameplay. Generally, people enjoy playing the same game over and over again. This can be seen in most of the popular games such as Hearthstone, Call of Duty, Counter-Strike, League of Legends, Dota. The list just goes on and on. But one of the things that all of these have in common is they're multiplayer. And that general idea of playing against another human and having that random element of what's the human going to do is kind of a really exciting way of approaching gameplay. But obviously, when you're playing either a single player game or just a game on your own, you don't have that element, and it just becomes a very stale sort of experience. And even some multiplayer games, such as Diablo 3, kind of fall short in the multiplayer side. After you finish the initial run through of Diablo 3, it kind of becomes a tedious grind, really, and it just becomes more of a job rather than an actual game. So that's kind of why Diablo 3 was received kind of really poorly. Our task was to make a racing car game, and this was all from scratch in our team. And obviously, how the idea is, how do we make something which is inherently repetitive feel less repetitive? Because obviously, going around a track loads and loads of times, racing against one another after you finish that first time when you get your best time or you beat your friend, kind of gets stale because, oh, okay, I've done it now. So our main focus was developing a game which felt different every time you played it, and our artist came up with a really ingenious solution on how to do this. And this is our initial approach to developing an AI system which allowed for multitude of ways to play, and it would be very random every time. And this was basically based off of the Mad Max movie, where the cars were trapped inside this huge sand tunnel and they were just racing around in it. And we had sort of a similar idea where a sand tunnel would be controlled by an AI, and it would just randomly go around the map, and the cars inside it would have a set speed and always be inside this tunnel, and the tunnel would always keep them inside it, and if they hit the edges they crash and burn or what have you. And the reason why this is such a nice idea, and why we wanted to do this initially, is because it allowed us to have this huge environment, and we could make just one level, and it would always feel different because of the way the paths were structured around the AI. And we could also have more of a traditional approach to racing car games, where we could set up waypoints for the AI to follow, and we could also use weighted values to ensure that the AI would follow certain trajectories. So if we needed to do a certain event like run over a ramp or something like that, we could set up a small line of nodes or what have you to line up with a jump, so that it would always have this sort of smooth kind of flow into a jump rather than just coming across and cutting over it. And another advantage of doing it this way was that we would have one camera, and that would mean more screen real estate. So instead of having a screen split up into 4 separate segments, we would just have one big screen with all the cars in it, kind of like most indie titles currently. And it would allow the artist a little bit more flexibility when it came to modelling the actual cars and the environment. Before we go on to the actual implementation, I'd like to talk about A-Star Pathfinding. It was originally developed by Niles Nielsen, a professor at Stanford University. He developed it for his robot Shaky, and the idea was for the robot to walk around the room without bumping into things. The algorithm itself basically is a first best search, which means it just finds the first path which actually leads to it and then uses that. But it does explore all the options available to it. Lots of games like Sims 4 use A-star pathfinding, and also RTSs use A-star pathfinding. There's lots of examples of it being used in games, and I'll just go over really quickly how the actual algorithm works by showing it in this example over here. So basically we'll start by defining the distance between each node. So in this case, let's go from this node here, so 1 1 1 1, and then because of these diagonal ones there'll be 2 square rooted because of Pythagorean theorem, so it'll be about 1.4, and then we just times this by 10 to give us a nice integer value, and that gives us the distance between each of the nodes. So if the AI moves diagonally, it'll be moving at a cost of 14, and if it moves horizontally or vertically, then it will move at a cost of 10. So this is how we set up the AI itself, and what the AI will do is look at all of these nodes which are on the outer set, on the open set, and then it will see which one is the lowest value, and then choose that one and explore it, and then add that one to the closed set, and then it will continue and look at all the different ones. Key thing to look at here is, although we have several nodes which are the same lowest value, what the algorithm will then do is look at the lowest oh sorry, I haven't explained what these values are, these ones in the corners. So this value in the top corner is the G cost, and this is the H cost, which is the heuristic value, which is the distance from here to here, and the G cost is the distance from here to here, and the F cost is the total of the two. So what it looks at is the cost from that node to the distance, so it will choose the one with the lowest H cost, and then the algorithm continues and progresses, and it just continues. Another thing to note is when we open up different sets and add them to the closed set, the open set will automatically adjust itself. So for example, what happened here was, as you can see here, this value up here is kind of incorrect because we can see that it's only 1, 2, 3 spaces away, which should mean it's 30. But when we find that new path, it then updates itself. So that's another key thing to understand about A-star pathfinding, that it does update its open sets. And then we just continue, and now we have values which are lowest by 62, 62, 62, and we have 68, and then we find the lowest path. And what you can see happening here is it finds the straight line to it, and as the H cost decreases, then the F cost will, as the H cost and the G cost interact with one another, basically the F cost will stay the same, but the closer it gets, the lower the H cost is, and then it finds its target. The implementation itself, basically we started by creating the smallest possible part of it, which is the node itself, and we took into account the things we'd need, like its weight, whether it was terrain or not, its position in the world, and then we just set up a simple grid, which is a 2D array of all the nodes which we would use, so the grid could be varied in size based on however big the environment was. Then we began experimenting to implement the A-star algorithm, and we came up with this simple formula here. But obviously the issue with this is it becomes very ineffective when it comes to larger maps, and so what we did was updated it with a heap, and that meant that we could have larger maps and it'd still take into account all the different values. And finally we implemented a state machine so that it could work. Basically it would switch between different states, and generally it would be in a state of wandering, whereby there is a circle around the AI which has a target location which traverses around this section of the circle, and the AI will always follow this, so it would always be random. and then it would switch to different states, and depending on which state it was in, it would affect the behavior. Unfortunately, partway through the project itself, we had to change our approach completely because we needed to implement tracks. Obviously, we wanted to keep the original idea alive, but there was no point in having an A-style pathfinding for a track-based game, because what's the point in having it pathfind a track? We could just set up a waypoints and it would just follow it, but then there's too much work for not enough payoff, and it doesn't work really. So we came up with a new approach, which is using Catmull ROM splines, which basically take into account several nodes, and what these nodes do, they're all interconnected with one another. And what we're trying to do is get an AI which will calculate a path through these nodes, and based on the path, walls will arise around sections of the map that the player can't go through, and it will still have very similar feel, but it won't be as effective as at being random as our original approach. Whereas our original approach had lots of different outcomes, this one has, for 5 nodes, it will have about 120 different ways a lap will pan out. So just in conclusion, summing up what has happened, obviously we have changed our original mind, but there's no point in holding on to ideas which don't fit the task at hand. So it's really good that we've had such great leadership from Alejandro, who's helped basically everybody in the group sort out their different aspects of the project, and it's good to have that sort of team side of thing. I've also uploaded a video on the actual AI itself, and if there's any other questions, just please don't hesitate to email me. Thanks very much. Bye.